Okay, let's read the question number 2 of a word problem, periodic word problem. Continuation from yesterday where we did the Ferris wheel question. Let's underline the most important parts. Let's start with a mass being supported by a spring so that it rests 50 centimeters above the tabletop. So at rest it is 50 centimeters above. Let's underline that. As shown in the diagram below, the mass is pulled down to a height of 20 centimeters above the tabletop. So it's pulled down and released at time 0. So that would be a starting point. It takes 8/10 of a second for the mass to reach a maximum height. And the maximum height it attains is 80 centimeters above the tabletop. As the mass moves up and down, the height h in centimeters above the tabletop is approximated by a sinusoidal function of the elapsed time t, underline t, for a short period of time. We are to determine the equation for the sinusoidal function that gives h as a function of time. And this was a 4-mark question on previous exam. So what we'll need to do is graph this relationship. So on a piece of graph paper, let's go get some graph paper. Okay, on your graph paper, let's label the x and y axis. The x axis would be time in seconds. The y axis would be the height. The height in centimeters. The title would be the boing boing question. Okay. Let's draw a y-axis and an x-axis. Okay, just like the graph we did yesterday relating height versus time for a Ferris wheel, we'll need to establish 5 key critical points on this graph. So if we go back, we see that the spring is at rest 50 centimeters above the tabletop, but the mass is pulled down to a height of 20 centimeters above the tabletop at 0 seconds. So we're actually going to pull this spring down until the height is 20 centimeters above the table, and that's at time 0. So that's where we're going to start. So the minimum height that this block will attain is 20 centimeters. Let's go up by increments of 5. 5, 10, 15, 20. So 20 centimeters is the minimum. Okay, so we're going up by increments of 5. And if we read on, it says it takes 8/10 of a second for a mass to reach its maximum height. So we know one of the points right now. One of the points on the graph is the point 020. At 20 seconds, we have a height of the block of 20 centimeters. So let's label that point. I've labeled it with a smiley face. Okay. It says that this block, once it's released, takes 0.8 seconds for it to reach its maximum height. So we have a minimum here at 20. If we count 0.8 seconds, I'm going to go up 10 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At 10, I'm going to call this 0.8 seconds. Okay. And I'm going to count up by 5 along the y-axis. So it's 25, 30, 35, 40 centimeters, 45, 50, 55, 60, 65, 70, 75, 80. And as we said before, it takes 8/10 of a second to reach a maximum height of 80 centimeters. So at 8/10 of a second, we can plot a maximum height here at 80. Now, just like yesterday with that word problem, I encourage you to draw the maximum and minimum axes for the purpose of finding the equation a little easier. So we'll draw a max axis here at the maximum value 80, a min axis at the minimum value 20, and we might as well draw a central axis at this point, which is the direct midpoint between 80 and 20. So 80 plus 20 is 100. 100 divided by 2 is 50. So at 50, we have a central axis. Let's label that as 50. Okay, once you see that these 2 points are established, we should be able to find now a third point. Notice that the maximum at 8/10 of a second is the midpoint of the next minimum. We should be able to determine the period at this point. 0.8 seconds is half a period from min to max. So another 0.8 seconds is when the next minimum would occur. So over here at another 10 squares, we have 1.6 seconds. At 1.6 seconds, we can say the next minimum occurs if this spring is in constant motion. So now we have 3 points on the graph. As I said earlier, you should strive to have 5. Directly between, in the middle between the minimum and the maximum, we should have a central value. Halfway between 0.0 and 0.8 seconds, we should have 0.4 seconds. 1, 2, 3, 4, 5. Here is 0.4 seconds 50, which is halfway between 80 and 20. And then at 1.2 seconds, 1.2 seconds, that was 0.4, we should label that. We'd have another midline value right here. So the same sinusoidal pattern as what happened with the Ferris wheel question happens here. We have a minimum, 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 minimum until we reach this midline value, and it bends such as a maximum, and then minimum again. At this point, we are ready to establish an equation for A sine of B x plus C plus D. So let's do that next. Let's write the sine equation first. Y equals A sine B x plus C plus D. A is the amplitude, or called vertical stretch. If you look back at our graph, the distance here between the mid-axis and the max is exactly 30 centimeters. So that would be our vertical stretch, 30. So let's call A 30. B is the horizontal stretch or compression. This graph definitely has been stretched versus previous graphs, it appears, but 1 seconds might lead you to think otherwise. Let's find out for sure by utilizing a formula that we referred to last day, which requires us to equalize the period to 2 pi over b. We know that the period on this graph from this minimum to this minimum is 1.6 seconds. So we can say 1.6 equals 2 pi over b, cross multiply, or multiply both sides by b, and we get b times 1.6 equals 2 pi. And now we divide both sides by 1.6 and we get b equals 2 pi over 1.6. And that's fine to leave our b value as a fraction like that. So we have a and b now. C. For C, since we started off by looking at the sine graph, we want to find a starting point. So looking back at the graph, a appropriate C value would be this point right here, as it coincides with the starting point for the regular sine graph. So I'll call this a possible sine starting point. Now that starting point, which is usually at 0, 0, has been shifted to the right. It's been shifted to the right 0.4 seconds. So therefore, we would call the C value 0.4 units right. And the D value, which is our midline value or vertical shift up or down, this central axis has moved 50 units up. So 50 units up would translate into a vertical shift up 50. So the D value would be 50. Now we're ready to write our final equation for cosine. For sine, which would be y equals a value of 30 sine of b 2 pi over 1.6 x. C is 0.4 right, so it's 0.4 right, so it'd be minus 0.4 plus 50. Okay. That's just the way we would enter it in our calculator. Now we should be saying this final answer in appropriate functional notation, which is relating height to time again. So we'll want to just fix up this final equation as height with respect to time equals 30 sine of 2 pi over 1.6 t time minus 0.4 plus 50. And this final equation would allow us to find out the height of the block at any specific point in time.